Welcome to this demonstration of new meta-uni features, specifically the loci and talking boards. So a locus is a meta-uni node dedicated to a particular mathematical topic. The one that's active at the moment is LC001 on matrix factorisations. A locus hosts expository content such as talking boards and is meant to serve as a place for shared mathematical activity using the whiteboards and the voice channels. So to put yourself in a voice channel, you need to open Discord, put yourself in the general voice channel before you enter the Roblox world. And make sure you've registered your Roblox username in the Discord server as per the instructions on the other parts of this page. A locus may have associated office hours. These aren't the real office hours. I'll be advertising those there later on, or you can check the TRS Discord for them. During those office hours, I'll be in the Roblox server and able to answer questions about the content of that node. So without further ado, let's jump into the Roblox world. So there are two sets of boards in here at the moment, one on matrix factorizations, a broad introduction, and one on exterior algebras. This recording will just have the content of the first set of boards. So you can see here, that's the first set of boards. There's another set in the distance over there. And to make the talking boards work, you simply click play. When the first board finishes, the control will pass to the next board and so on in sequence. These boards can be annotated like normal whiteboards, so you can write on them when you're viewing them with other people, subject to the administration controls that are active for all boards, of course. So I'll go ahead and play this. Just note that the best way to consume this is either to click on it to see the full screen view, or to use the scroll wheel, the I/O keys, or pinch in, pinch out on an iPad to put yourself into first person view. So I'll be switching in and out of that while making the recording. So I'm going to click play now. Note that everything that's happening on the board and the audio is pre-recorded. The live me is not going to be interfering in this except to move the camera around. Welcome to this quick and dirty introduction to matrix factorizations. A matrix factorization is a square root of a function. So this is some function, let's say typically a polynomial or a power series. Most of the time, such a function won't have a square root in the usual sense, just as -1 doesn't have a square root in the usual sense if you're considering real numbers. Now the key to constructing square roots of -1, as you well know, is to think about -1 not as a number but as an operator, and not as an operator of multiplication by -1 on R, but as an operator of multiplication by -1 on R2. That is, to think about it as a 2 by 2 matrix. Now, if you think about it that way, then -1 is the operation of rotation by pi. And that operation has a square root. And that operation, of course, we call I, if we think about C as being R2. So the point of that observation is that, first of all, you can construct interesting square roots of functions, in this case a constant, by considering that function as operating on some vector space, or more generally, a module over whatever ring of functions the function belongs to. And secondly, it's not pointless to do that. Of course, we believe in the importance of complex numbers, and they appear in nature. So it turns out that nature loves such square roots. Not only complex numbers, which appear in quantum mechanics as well as many other places, but more exotic examples. So a very famous example of an exotic square root was discovered by Dirac. Dirac was trying to understand the relativistic behavior of electrons, and for that purpose introduced the following square root of a differential operator called the Laplacian. So the Laplacian in this case is acting on four-dimensional space, or rather functions on four-dimensional space. The fourth coordinate is identified with time, and it's given these coefficients. C is the speed of light. Dirac observed that if you consider the following first-order differential operator, that will give a square root of the Laplacian, provided these coefficients gamma are taken to follow the following equations. Of course, there are no numbers satisfying those equations, but that won't stop us. There are operators on some vector space which follow those equations. In fact, Dirac found a solution of these equations in 4x4 matrices. If you have a solution to these equations, then this equation holds, and you found a square root of the Laplacian among first-order differential operators on vectors of functions. Now the right-hand side here isn't a function, but so it doesn't quite fit into the paradigm that I've outlined here. But if we just take, instead of differential operators, the operation of multiplication by xi, and keep the same gammas, let's suppose we take them to be the 4x4 matrices that Dirac found, then what we see is that we have on the left-hand side a square matrix, 4x4 matrix, with entries which are polynomial functions. And when we square it, we get a diagonal matrix which has the sum of the xi squareds on the diagonal. Okay, so this is an interesting example of a matrix factorization. This is our function f, and this here is some operator delta, which squares to give f. Okay, so the upshot here is that you can find interesting square roots of functions as long as you take the square root to be allowed to be in a space of operators on some module over the ring of functions. And such a square root is called a matrix factorization. So what good are these square roots of a function? Taken individually, they are perhaps actually not that interesting, but taken together, the collection of all square roots of a function f form a category, which is denoted HMF of f, H for homotopy. So this is called the homotopy category of matrix factorizations. And this category turns out to have a rich structure for certain classes of functions f, and reflects what you might call the inner life of the function. Now, by this definition of the inner life, a function which defines a submanifold, so something which has at every point of the vanishing locus some partial derivative of f being non-zero, let's call that f1. The homotopy category of such a function is just the zero category. So such a function has no inner life by this definition. Perhaps the next most interesting example is a node that has a slightly interesting associated category, and then perhaps a cusp. As the singularity becomes more interesting, so a singularity just means a point P where a function vanishes and every partial derivative vanishes. Which means in particular that near this point, the set of vanishing points of F2, that's an algebraic variety, but not a submanifold near P, as you can see clearly in this picture. If this gradient were non-zero, so some partial derivative were non-zero, then it would be a submanifold. Okay, so this is also a singularity. And the more interesting the singularity, the more complicated it is, the more interesting and complicated is this homotopic category of matrix factorizations. So this equation here is yet more interesting. One of the good things about matrix factorizations is that it's easy to construct examples and it's easy to compute with them. A typical example is constructed as follows, given a presentation of the function f as a sum of products. I'm going to suppose, given operators theta 1, theta 2, theta 1 star and theta 2 star, satisfying some equations. The equations say that the theta i's anti-commute, the theta I stars anti-commute, and theta I anti-commutes with theta j star, provided I is not equal to j. So this is the Kronecker delta, which is equal to 1 if I is equal to j, and 0 otherwise. So such operators can be constructed as matrices or as operators on the exterior algebra. I'll just assume that they're given. Then I can construct the following operator using the theta i's. And I claim that this is a matrix factorization of f. Now that's a calculation that involves these three relations, and it's the kind of thing that can only be understood by doing it yourself. So there's a board set up over there. I encourage you to go over and do this calculation using those relations, and then continue on board 4. Here's an example of a matrix factorization constructed in this style. Such a matrix factorization is called a causal matrix factorization. So consider the following polynomial g in 2 variables, n is some integer greater than or equal to 1. This is a symmetric polynomial in the sense that exchanging u and v leaves it invariant. And so it's a property of symmetric polynomials that any symmetric polynomial can be written as a polynomial in the elementary symmetric polynomials. So let's say h. The elementary symmetric polynomials in 2 variables are u plus v and uv. So there's some polynomial in 2 variables h in those elementary symmetric polynomials, which gives g. Now if I take the function f, which is two copies of g subtracted from one another, Well then, clearly, if I put x1 plus x2 equal to x3 plus x4, and x1, x2 equal to x3, x4, then f is 0. That means f belongs to the ideal generated by those two equations. In other words, f can be written as a1 times this generator for some polynomial a1 plus b1 times the second generator for some polynomial b1. Well, this is exactly, well, I guess that wasn't my notation earlier. I called that a2, didn't I? So if I take this to be my b1 and this to be my b2, this is an expression of the form used in the previous board to construct a del So that's a matrix factorization of this original equation, f. And in fact, this matrix factorization is the foundation of a particular kind of not invariant called Khovanov-Rozansky homology. So this is a non-trivial matrix factorization, and it's been widely studied and used in the study of knots. So that's it for this introduction to matrix factorizations. Matrix factorization is a kind of square root of a function. They can be constructed using presentations of the function. In this case, you see that what I'm using is a particular symmetry of the function to do with exchanging variables. So symmetries of a function will give rise to matrix factorizations. These matrix factorizations have an interesting structure, and their homotopic category is a kind of invariant of a singularity, which probes the inner structure of that singularity. Thanks for playing.